In this chapter, we have discussed about Lagrange equation, its derivation from D'Alembert's equation, a principle, then what is that principle and many terms related to that. So, now we have reached to the last part of the unit, that is applications of Lagrange equation, like how we will be applying Lagrange equation in various systems to find the equations of motion. And I will be dealing with 3 applications and rest 3 will be done by Isabella in the next class. So here I will be doing Atwood machine, simple pendulum and double pendulum. So Atwood machine and simple pendulum, Nishant sir had already taken this. He already took the class. So I hope it will be easy. So we will start with Atwood machine. Before that, let us quickly revise what is Lagrange equation. So can someone tell me Lagrange equation? Marcel.
Dou L by dou Q dou K minus
d by dt
of dou L by dou Q dou K minus K dl by check dou L by dou Q K.
Yes, it is d by dt of dou L by dou Q dot j minus dou L by dou Q j equal to 0, where Q is generalized coordinate, and we can find L by using the equation T minus V, where T is kinetic energy and V is potential energy. So we will be using this in various systems and we will be finding So the first application is Atwood machine. So this has been already covered in the class. So the figure is like this. So this setup consists of 2 masses, M1 and M2, and it is held together by a string of length L, and we have x1 distance from the equilibrium point for the mass M1 and x2 is the distance from the equilibrium point for mass M2, and we have x1 plus x2 equal to the total length of the string. And if you want to see I hope you saw it. 2 masses are there and there is a frictionless pulley, and that is being diagrammatically represented here. So this is the thing. And now we are using the Lagrange equation to find the equation of motion. For that, first we have to find this L. So what was the equation for L? Igneous, what was the equation for L? Yes, it is T minus V. So we want to find T. T is equal to kinetic energy, and Abhishek has already said about the equation for kinetic energy in the first seminar. What was the equation? Half m x1 dot square plus y1 dot square. So here it will be half m x dot square. So for first mass it is m1. So d1 will be equal to half m1 x1 dot square. So this is our d1. Then for mass 2, t2 will be half m2 x2 dot square. But here we have an equation x1 plus x2 equal to L. So from this we can write x2 is equal to L minus x1. So this can be written as half m2 into, instead of this dot I am taking it as d by dt. So d by dt of L minus x1 the whole square. So when I do the derivation, so it will be half m2 d by dt of L. L is a constant, so it will be 0. Then we have d by dt of x1. So it will be x1 dot. This is our t2. So we got t1 and t2. So our kinetic energy will be x1 dot square. So from this half and x1 dot is common, so we are taking it outside. Half. We will have m1 plus m2 inside. Plus m2. Then x1 dot square. So this is our kinetic energy. Now we have to find the potential energy. Hope it is clear. If you are having any doubt, you can ask in between. So next is we have to find V. So for V, for x1 it will be V is equal to mg. It is x1. So mg x1 v1. Then v2 will be mg x2. X2 we have L minus x1. L minus x1. So this we can open in the form mgl minus mg x1. So the total V will be equal to mgx plus mgl minus mgx1. So this is m1, this is m2. If I am making any careless mistakes, please do inform. So here we can see this is common, gx1 and gx1 is common, so I am taking it together. So V will be equal to m1 minus m2 gx1 plus mgl into g. So this is our fourth equation, that is our V. So here you can see that we have got our kinetic energy and potential energy, and here we have only a single variable. What is that variable in both this equation? X1. So x1 is our generalized coordinate, and we have to find our Lagrange equation. Lagrange equation for this one. So our equation is d by dt of dou L by dou x1 dot minus dou L by dou x equal to 0. So first we are going to find dou L by dou x. Before that I will write L together. L is equal to t minus v. Our t is here half m1 plus m2 x1 dot square, then minus m1 minus m2 gx1. Here this term you can see that there is no variable part in this term, so we are neglecting that. I hope you understood. So it will be cancelled. Then we have our L as this one. So we are substituting in this. So first we are finding dou L by dou x. So what will be dou L by dou x? Can someone help me, Deepika? What will be dou L by dou x? From this. Here we have a term for x1, right? So here it is x1 dot. So we don't need to look for that. Here what will be the derivative of this term? Yes. It is minus m1 minus m2 g, because we are derivating with respect to x1, so other terms will remain there. Then we have find dou L by dou x. x1 dot. So from this, here we have x1 dot in only this term. So derivative of x1 dot square is 2x1 dot. So this 2 and 2 will get cancelled and we will have m1 plus m2 x1 dot remaining. Is that clear? Next, we have to find the derivative with respect to time. And for that, d by dt of dou L by dou x1 dot. That is time derivative of this one. So what will be the time derivative of this one? Yes. It is m1 plus m2 into x1 double. So we got all the values. Now we are substituting in this equation. So it will be m1 plus m2 x1 double dot minus of minus will become plus. So m1 minus m2 into g will be equal to 0. Now we want to find the equation for acceleration. This is our acceleration. So we will bring all those terms to the left side. So it will be minus m1 minus m2 g divided by m1 plus m2. So this is our equation for motion for this Atwood machine. So you can see the equation there as well. I hope it is clear. If you are having any doubt, you can ask in between. No doubt, right? So can I move on to the next one? So the next one was also covered in class by the sir. So with the symbol pendulum, I hope you all know the setup of a symbol pendulum. So symbol pendulum consists of a mass of m1 and it is held using a string of length L. So this is the figure.
You mentioned about the act right? So
Setup is symbol pendulum.
actually it's a right?
So the next system is symbol pendulum and we have a string of length L and mass of m1. So it is making a movement and we have our angular displacement as theta 1 and we are taking our equilibrium point from here so that this distance will be y and total distance is L and this left over part we are taking as h and this will be x. Okay. I hope this figure is clear. So what we first want to find is kinetic energy. So V is equal to half m into x1 dot square plus y dot square. So can someone tell me what is x here?
Just a moment. That
What will be x1? Nandana, what will be x1 here? This. We have theta 1 here. So it will be L sin theta. L sin theta. Why this L sin theta? Because we need to get this distance. This is same as this one. So opposite by adjacent is sine. So it is L sin theta. Similarly, what will be y? Yes, it is L cos theta. Then we have to find x dot and y dot. So x dot will be L cos Then in the same way for y, minus L sin theta dot. So we got x dot and y dot. We have to find the square of it. So E is equal to half m into x dot square will be L square cos square theta into theta dot square plus this minus will go when we square it. So L square sin square theta into theta dot square. So this is our t. So from this we can take these common things outside. So it will be half m L square theta dot square. Inside we will have cos square theta plus sin square theta is equal to 1. So this is our kinetic energy. Then next we have to find potential energy, that is V. V is equal to mg into height. So our equilibrium point is here. So this is our height we are considering. So mg is h. So h from this we can find as L. This is the total length. Total length minus y will be our h. So that is mg into L minus y. And we have our y as L cos theta. So it will be mg into L minus L cos theta. So when we open it, we will have mgl minus we are taking this outside for once. mgl into 1 minus cos theta. So mgl minus mgl cos theta. So this is our B. So L is equal to T minus V. L we have half m L square theta dot square. So L is equal to half L square theta dot square minus mgl. Minus or minus will become plus mgl cos theta. Here also we are having only a single variable. That's our generalized coordinate. And here you can see there is no term. This term is not having any variable. So that is negligible. So L is equal to half cos. So this is our L. Now we have to substitute in our Lagrange equation to find the equation of motion. So first we find dou L by dou theta. So what is dou L by dou theta? Lakshmi, what is dou L by dou theta? mgl minus sin theta. So that is our dou L by dou theta. Then we have dou L by dou theta dot. dt. What is dou L by dou theta dot? This one. ml square theta dot. So we got both the terms. Now I will be substituting in the equation. So equal to 0, and we are finding for this term acceleration. So we are bringing all the other terms to the right side. So it will be theta dot will be equal to minus mg L sin theta divided by ml square. So L and 1L get cancelled, m and 1L get cancelled. And when compared with sin theta, our theta is very large. So we can write this sin theta as theta only. So then theta double dot will be equal to g theta by L. So this is the equation of motion for our simple pendulum. Is that clear? Is there any doubt, Anisha? So this is our equation of motion for the simple pendulum from Lagrange's equation. So next we have a double pendulum, which is in this setup one more mass is added.
I think you can